Hey, hello everybody. Welcome to another class. Let me check if everything is working fine here. Let me go here and check YouTube. Testing, testing. Hello, hello. Testing, testing. Hello. Hey, hello everybody. Welcome to another class. Okay, so the sound is good. So in today's class, we will learn how a computer can store and deal with different type of information. Just a second, sorry, I got a message here that my screen is not healthy. Let me see what is going on. Hello, hello, testing, testing. Okay, hello, hello. Hey, hello everybody, welcome. Okay, somehow my connection is not good, so the streaming is not going to be very good. But anyways, I hope, I'm expecting most of the people who watch this offline. The reason that I do live videos is just to focus, to concentrate more. When we try to record, we try to be perfect, we try to go back, do editing, and live make me feel like I'm in a classroom. It's like a live conversation, and whatever goes wrong, goes wrong. So that is the goal here, to be like a closer to a real as possible. So we learned up to the last class that a computer can only store information as binary. Everything has to be translated to bits and bytes. We learn about some different like numeric system and how to convert between them. Like I said, the last class is very skippable, like you don't need to understand, but today we're gonna see that that knowledge is used for some understanding. So how, knowing that everything is a sequence of bits, how can a computer distinguish between different type of information? For example, text. We are like type letters, like words, and how we know, or how, not we, how a computer know that that information that is stored is a text. How it does know that is a video or is audio. That is what we're gonna cover today. And I hope I can remember, everything will be layers of abstraction. We are like looking to this content from like 5,000 feet high, and we're gonna slowly going down, uncover layers and layers of abstraction, but we don't need to go all the way down to understand. So it's kind of, I prepare you to know enough to drive a car, but you're not going to be like mechanical engineers. We don't need to explain or know everything that is under a car, like it's the same with software engineer. We can't know everything, but we have to understand how to use the thing. So that is the idea. And with AI, I think that gap is even easier to cover. So let's go here. Everything is a sequence of zeros and ones. All data has to be translated to numbers and has to be stored as bits and bytes. So regardless of what kind of information, looking to the metal is just zeros and one. The zeros and one can be depend of the device or memory, can be different, like physics, could be like magnetic points, could be voltage, could be lights going to one side or the other, but everything that has to be like two states. For text, so up front, every computer has to be informed, this sequence of bits is a text. This sequence of bits is a video. This sequence of bits is a audio or whatever. Otherwise, the computer cannot like understand it. The simplest way to understand is for text. What we do for text, we map every letter or every character to a number. And then there is a table that the computer will like convert to and from those numbers to the letter. When like computers start, they have to create a master table to convert the text. So let's see how everyone else has to store and read like text. So they build this AskII. It stands for other like counts. Oh, we want to have our character as well, because not everything is just the American alphabet. There is so many other symbols, different language that the computer would had to adapt it. So if we go here and open this, is a ask table. So if you look down here, now see that we learned in last class about decimal, octal, hexa, and binary. That's why I taught you about those number system and how to convert between them. Look how cool it is, because depending where you are, you want to see the number as one of those. And we can see here easily that binary uses way more information, way more space, way more bits. So there are some characters like control, like some is an empty character. And if you go down, we'll see all the special characters. Open, close parentheses, star, plus. Do you see? Those are the numbers. So if you are talking about decimal, star will be 42. 0 will be 48. In octal will be 066. Just reload it here. If we go to letters, you see that capital A or uppercase A is 65. B is 66, and so on. Lowercase 97, 98, and so on. So this is how, back in the days, every text was stored. For example, if we have the word love, love will be Love. So what you have to do, come to this table and look, what is the number for lowercase l? 76. Lowercase o, 111. Lowercase v, 118. And lowercase e, 101. If we represent the same number in binary, it will be this: 76, 111, and now we learn next class how to convert. A good exercise. Do it so you can learn. So this one, we can just do the math here. This is in octal, this is in decimal, this is in hexadecimal. The good thing that we learned in last class is not to really know that conversion, but if we see something like this, you don't get like lost about what the heck is this, octal, decimal, binary. Now you know, it's just numbers representing the different number systems. They all have the same value. It's like kilometers, miles, or Celsius and Fahrenheit. The same values can represent with different numbers, different amounts, but they are convert each other. So back here, for several decades, this was the main table of conversion. But then computer get more popular, and we had to accommodate all other languages and symbols. So then something new came that is called Unicode. So Unicode went way beyond those basic ASC, II, and now we have 140,000 characters to cover all the different languages. So Unicode is kind of the standard. And UTF is how we store this. So UTF is the encoding. So usually we talk about Unicode, UTF. Most of the time we say they're the same, but one is the standard, the other one is the encoding. So to do the encoding, we use 1 or 4 bytes per character, because now we don't have only 256, we have 140,000. So now we need way more bits, up to 4 bytes, sorry. One thing that they did is they kept the same characters numbers for ask in this UTF. So this way there is a like backward compatibility. All the numbers for those American letters and numbers, they are the same. However, for all the other language, there is a big table. For if we go here, for example, this is the Unicode table. The ask table, we could just see in one screen very easy. This is the extended one. There is some extra symbols like those things here. But still, we can just look like this. 140,000 symbols has to be organized in a different way. So here, I want to see, let me get something here like Samaritan. No idea what that language is. But if we click there, there is some documents and we can see what are the symbols. What are the characters there? And everyone has the number. So this is the new standard. Today, oh, sorry, I closed it. I should keep it open. So today, this is kind of the universal way and the most common one using web application and all the system. Like you have to be ready to read, produce, and send message in Unicode. Because now our system can support, oh, where is it? Here, Unicode chart. Let's get something different here. Let's see if I can find something interesting. What else should I get here? Egyptian. So look at this. We can go here and have all those characters. So now we can have a file that has those characters there. And now we can have the same word like here, love, with the characters for each one of the language. For example, Chinese. I am trusting AI because I asked them to generate. So Chinese, we have this character here. So in theory, if I get this guy, I should be able to come here somewhere and search for it. And let's see if I can go here. And it's going to tell me, no, I guess it's not this. So, oh, wait, maybe it is. No, not here. But we should be able to do this. Let me go here and say, let me just Google it. Unicode character. Is this? And then we can try to understand what is the meaning of it. Love. Be fond of, like. So, like everything else, sometimes there is multiple interpretation. So I hope AI or Copilot gave me a right interpretation. But this is the character, one of the characters for love in Chinese. In Japanese is another single character. In Hindi, Hindi is 1, 2, here are the characters, like 3 of them. We can even make try. Let's get this, go to translate, Google Translate. Hindi to English. And is there, love. Here is in Korean, so Korean looks like a stew character. So let's get this and let's go to here and then put like Korean. And let's see if we, oh, I already did the translation because got the word in English, so love. So it's correct. I don't need to do to everything, but just to show how the computer has to be ready to adapt to different cultures. Because not everything is just about regular alphabet that most of us know. Here's in Greek. He could like all this. Let's just see if it's correct as well. Let's go here and, oh, sorry, not the Greek. Oh, Greek. Salang. So let me see if it's there. Agape. So maybe there is different word for that. And this is what I want to understand. Everything has to be converted to numbers. And we should have a table or something to translate the numbers to what we need. I'm going to try to explain here all the abstraction that happen when we press a key in our keyboard and how we see that letter in the screen. So we can have an idea. So here there is some low, like kind of low level explanation. So when we press the A key in the keyboard, there is a board, a keyboard board that identifies. Imagine that there is like a matrix that there is a cross that when we close that circuit, that signal is going to be sent. There is a keyboard processor that is not being shown here. So this information goes to your computer motherboard. The computer motherboard is going to do some conversion. This is an oversimplification, but just to show you how many layers of abstraction we do have, just to have a simple key to appear in our screen. So here we are using ASCII. So A, when we get this one electrical signal that represents this binary number, the computer says, oh, what layer is this? What number is this? 65. So 65 means A. And then there is somewhere as well a bitmap character to tell how to draw an A in the screen. And this happened behind the scenes. Like I said, we can drive a car without being a mechanical engineer. The same thing. We can type a text, we can type code, we can build an entire useful system without really need to understand all this. Back in the days when the first software engineer was not a term at that time. When the first programmers, they were using the system, they had to know all this because the level of abstraction was not as high as today. They had to, or even today, if someone working like low level thing, they have to deal with that. But most of us, we are learning here to working like, we are not learning here how to design and build a car. We are learning here how to drive a car, how to get a car from point A, load with thing, with passage or product, and then drive to other place. Computer engineer is different from software engineer. Computer engineer are the folks that work on this low level hardware like stuff. What a software engineer needs to know is, okay, let's just understand and be glad and thankful for all this abstraction that are already solved for us, but it's interesting to know that there is something below what we're doing. So never feel so important or your ego that high, because for everything that we do, a lot of smart people had to prepare the foundation for us. Okay? So this is just an abstraction. When we press A key, for us is nothing, but then you can see letters at the screen. Remember, a computer that doesn't really know what A is. Just know what there is a number, and I'm going to translate to this letter, and this letter has a bitmap character that I should turn on those pixels at the screen. So it's like there is and here, like I said, an oversimplification, because we can have different fonts, and those fonts could be just something like this, a pixel pattern, or could be a formula to draw that letter A. Okay, so next, how can a computer interpret an image? Will be very similar to a letter. However, instead of just have this fixed bitmap per letter, what we have here is, again, this is an oversimplification, but we can understand as an image is a composite of pixels. pixel we can descend as every dot that we can have in our screen. And every dot is like bright. And then we have the RGB, red, green, blue, because we know that most of all the colors can be is a combination of those three. So every pixel has three little dots that is going to be bright based on this combination. How much blue, how much green, how much red, it's going to glow. And then how we see the screen. Our screen is a matrix of pixel. Every pixel is going to be like the monitor is going to turn on little lights with intensity based on those three numbers. So what we do have here is, if we have the image like this very simple flower, it's a composition of pixels. For every pixel, we have three numbers. What is the intensity of red, green, and blue? And this is how the computer will get the sequence of bits. Again, it's an oversimplification. We interpret this. We'll talk with like other device, graphical card, and you're gonna tell, oh, I need you to draw the sequence of bits in this area of the screen, and then we can see the draw or the picture in our screen. If anyone is going to work in the image processing, then there is a lot to learn here. We could have like weeks and weeks and weeks of class to learn that. I never work in image processing. I had some disciplines in my master. I enjoy it, like do some transformation, like move and rotation and like copy and paste, thing like that. It's very cool. But at the end of the day, we are manipulating numbers. An image is a sequence of numbers. And then when we go here and we try to change the color, is this what happened? When we copy and paste, this is what happened. We get that area, we remove all those pixels there and then put in another place. When we get a brush and then we paint some area, is that what we're doing? We are replacing that pixel there with whatever the brush is doing, what color we are using. And at the end of the day, it's just a sequence of bits that the computer plus some software plus some hardware is going to interpret it to put in the screen. Everything we see here is like this. The computer is very fast drawing all this text, all this image based on this. This is what a computer does. Very simple thing, very fast. So this sequence of pixels can be stored just in a huge sequence of three numbers. Every pixel is three numbers. Every pixel is three numbers, and then how we have that that image is stored. For example, if our image has a resolution like horizontally vertical, this is what those numbers mean. 1920 for 1080. That means we have in horizontally like 1920 pixels like this. How many pixels we have? And in this way you have 1080. In my case here, I guess if I go to, let me see if I can show you. I am using a 4K monitor. So if you go here to where I go, display configuration, I can choose what resolution I want to use. So in this case, look, it's a huge resolution. If I change this, you see that the thing is gonna be like bigger. So that means my screen, this monitor is a ultra wide screen, has 3,440 pixels this way, and 1,440 this way. And every pixel here is gonna be drawn like multiple times per second using the RGB for this guy. And by the way, there are different ways to represent the image. This is a very complex thing. I'm just giving an example. So now we understand what those things means. How a computer can deal with image. It's just a sequence of numbers. Every pixel has three numbers, and then somehow computer know how to draw it in the screen. So there is a lot of things behind, a lot of abstraction. Like I said, it's level of abstraction. I'm not trying to teach here about details of image. It's just to give an idea how different type of information is stored and processed by a computer. If a computer does not know that this sequence of bits is an image, it's lost. Is that why, if, for example, in Windows, every file has extension? Excel file, there is a proper extension. Word file, there is a doc extension. Everything we need to tell the Windows what is the content of that file. And do exercise, get one file and try to change the extension. Windows will give you a warning. Well, if you change the extension, I may lose the ability to read this file. Because if you are, for example, if you get a Word document, something .doc, and then you change to txt for text, and you try to open it, your Windows will identify, oh, this is a text file, I need to give to Notepad, because Notepad is usually the default program to read text file. But when they try to read it, it's a Word document. So all the sequence of bits inside it is not what it know how to read. If you get a JPEG file and you change the extension to doc, for example, and you try to open, Windows will try to open that image in a Word document, and it's going to fail as well because it's like I'm trying to read an image as a text file. Is that why every file, so there is like different ways to tell the operational system or for the computer what is the content of that file. But without knowing the content, no computer will be able to deal with that file. Okay? So those are very visual. And now we go to, for example, audio. How a computer can store audio is the same idea. It's a bunch of numbers that, if you know about audio, is like a wave, and that wave has to be sampled in some interval. I'm not like an expert in audio. I never work with any audio process, but if you're going to work on it, you have to learn. Open a parenthesis here. Many times, as a software engineer, you have to apply your ability to build something in a different area. You're going to work in a bank. You have to learn about banking. You're going to work in an accounting company. You have to learn about accounting because you will build a solution for accounting. And a big parenthesis here. To go higher in your career is not just about knowing the technology side. It's knowing the business side as well. So this is one thing that motivates me to give this training, because now I want to make easier for people that is very good at the business side to take advantage of AI, to have a good foundation and be able to help build stuff, or even to build stuff itself, because that gap now is going to be kind of easier to cover. Sometimes I feel, oh, do you know, I am afraid that AI is developed like so fast that it's going to make my knowledge like useless. What I bring to the table, I had that dilemma already, but I realized, well, do you know, AI is awesome, is very helpful, but is far from replace a good software engineer, even a good junior software engineer. I guess most of people take that wrong. It's going to augment us. And as more people know about it, know about the foundation of software engineer, we're going to make more advance on it. Because now they're going to realize, whoa, what AI is really doing, I can understand, I can review, I can push back. And I realize, whoa, there is no magic. There is a lot of crap thing that is being generated by AI. And if I'm a crap software engineer, my solution will be crap. And that happened forever. Why there is so many problems in software? Because most of the time we don't know the business very well, and we have bad engineers. People that was like up to 5 years ago, people was take like a 2, 3 weeks, 4 weeks training and become a software engineer. Imagine if you were doing that in like for a surgeon, for a lawyer, how many trouble you'd have. Cool? Okay. So going back here, closing the parentheses. So sound is same thing. There is format that we're gonna store some information. How can we represent that sound? So when we save a file, .wav, there is many different ways to store it, to process it, but the same idea. It's a sequence of numbers that is going to tell us how to read that sound. It's similar to a partition, like music partition. Like I'm very bad in music, but the same thing. We have symbols that can tell us how to play a music. We have numbers that tell us how to play a music, how to play a sound. That is the idea. A video is a combination. We have images, a sequence of images, because one video is nothing but just a sequence of image, and then audio on top. Is that why, like in video, we have like multi-channel? We have music 1, music 2, because we can have different sounds, right? If you do any sound editing, it's like that. We can have multiple sound channels, so we can input like music, background, special effects, and then we have the frame by frame, like we call every image in a video frame, and then we understand like 20, 40, 60 frames per second. That means for every second of video, how many images we have, how many frames we have. As more frames as you have, more details, more good transition. If you have a small frame, like frame rate, the image maybe is not, the transition not clear. So that's why when you play games, like you have like that FPS, like frame per second, because if you have a good graphic card, you can push the limits and have a higher frame. But at the end of the day, whatever we are storing or processing will be numbers. And then every area, we have some science behind to allow that to happen. Okay, and video, there is way more, like all this thing here could be hours and hours to go deep into, like even image, there is many different ways, variation. So there is compressing, there is like, I just give like a very oversimplification, but good enough for us to understand. Regardless of the data that computer is doing, it's going to be a sequence of bits that we need a way to translate it. And this is already a solved problem. We, as a software engineer, we don't need to, because this is already out there. Unless we are pushing something new, we can just use as to get a car and drive it. Cool. So that was the goal for this first part, is just to give some light foundation to understand how a computer can store